Alright, we're going to look at 1.6 function operations and composition of functions. We're going to start with addition of functions. So if we have f plus g of x, we can write this as f of x plus g of x. And so let's say our f of x function is x squared plus 4x, and our g of x function is square root of x plus 2. We are going to add these together, so in for f of x we're going to substitute in x squared plus 4x, and in for g of x we're going to substitute in the square root of x plus 2, and f of g of x equals this. If we add to this an h of x, we have a 3x minus 5. So let's say we have f minus x, f of h of x. So we're going to plug, I'm going to rewrite this. This can be rewritten as f of x minus h of x. And now we're going to substitute in f of x here. So x squared plus 4 is going to go in for f of x. And then for h of x, we're going to substitute in 3x minus 5. Now, since we have a subtraction here, we need to put our parentheses, because we're subtracting the entire quantity, not just the first term. So we'll distribute our quantity here. So x squared plus 4x minus 3x plus 5. Combine our like terms. So f of h of x equals x squared plus x plus 5. Now we'll look at a multiplication. So we have f times h of x. We'll still use our same equations from before, so f of x equals x squared plus 4x. G of x is the square root of x plus 2. And h of x is 3x minus 5. So we can rewrite this as f of x times h of x. And again, just substitute. We're going to substitute x squared plus 4 in for f of x, and 3x minus 5 in for h of x. And now we'll need to distribute or FOIL to calculate. So we have x squared times 3x, x squared times negative 5. And that gives us 3x cubed minus 5x squared, and then 4x times 3x, 4x times negative 5. So we have plus 12x squared minus 20x. Combining like terms, 3x cubed plus 7x squared minus 20x. So f times h of x is 3x cubed plus 7x squared minus 20x. And then the last one we have is division. So we have f divided by h of x. So substituting in, we can rewrite it as the function of x over the function of g. So x squared plus 4x over 3x minus 5. And that is as simplified as it goes. We do need to consider our domain here. We cannot have our domain cannot be 0, so we need to consider that. So we're just going to set this equal to 0 and find out what makes the denominator 0. So in this case, if x equals 5/3, then the denominator is 0. So x cannot equal 5/3. Alright, so we're going to look at composition of functions. And this is, we write this where a composition of a function is when we put a result of a function into another function. So we have f of g of x. And so it can be rewritten like this. And this is how I prefer to write it because it's easier to see that my g of x function, that answer goes into my f function. And so what you're doing is you're plugging your x value into the g function and getting that result, and then plugging that into your f function. So let's practice one. So the functions we're going to work with, we have f of x equals x squared plus 1, and g of x equals x minus 4. And so we're going to start by finding f of g of x. And so I'm going to rewrite it the way that I think it's easier to read. So I'm going to substitute in x minus 4 in for my g of x because that's what g of x equals. So using substitution. So now I have f, and I have my x minus 4 is in my x spot. So in my equation, any place there's an x, I'm replacing it. I'm substituting x minus 4 in. So my f of x function is x squared plus 1. In for x, I'm putting in x minus 4. Then I'm squaring it plus 1. So we have to FOIL this out. And that gives me x squared minus 8x plus 16 plus 1, simplifying that to x squared minus 8x plus 17. So f of g of x is equal to x squared minus 8x plus 17. So using those same functions, I'm now going to find the g of, erase this line here so I have some space to work. And I will use green. So g of f of x, just to show that they're not equivalent. So I have g, and then I have my f of x inside. So I'm going to substitute my f of x function into my g. So f of x equals x squared minus 1, so I use substitution. And now x squared minus 1 is going to go into my g function. And so any place that there is an x, that's where my x squared plus 1 is going to go. So I'm going to have x squared plus 1 minus 4. Combine like terms, we get x squared minus 3. And so these are not equivalent equations. Alright, so I have f of x is x squared plus 1, and g of x is x minus 4. And we're just going to look at f of g of 2. So I'm going to rewrite this so it makes more sense to me. So this is saying that I'm plugging 2 into my g equation. So I'm just going to bring this down. And I have 2 minus 4. So 2 minus 4 is negative 2. And now I'm plugging that result into my f function. So negative 2 squared plus 1. And that equals 4 plus 1, which is 5. Alright, so now we're going to look at composite functions with restricted domain. So we're going to look at the f of x of 1 over x plus 1 and the g of x as x squared minus 9. So we're going to look at f of g of x. And this is going to be f of g of x. And so I'm going to substitute g of x in for, I'm going to substitute x squared minus 9 in for g of x. So we get f of x squared minus 9. And then we're going to substitute, now we have f of x squared minus 9. We're going to substitute that in for x into our f function. So we have 1 over x squared minus 9 plus 1. Simplify. We have 1 over x squared minus 8. And so now looking at this, we need to take care of our denominator here. We need to ensure that it's never going to be equal to 8. Equal to 0. So what we're going to do is we're going to set x squared minus 8 equal to 0. And we're going to solve. So we get x squared equals 8. Square root both sides. X equals plus or minus the square root of 8. We can simplify that a little bit as x equals plus or minus 2 square root of 2. And so this means that in our denominator, this function works as long as x is never equal to plus or minus 2 times the square root of 2, so x cannot equal that for our domain. Alright, so here we have another function. We have another f of x that equals x squared minus 2, and we have a g of x equals the square root of x minus 3. And we're going to do another f of g of x. And so rewriting this as f g of x. So we're going to use substitution. So g of x is the square root of x minus 3. So bringing down our f. Straight substitution. So now we have f of square root of x minus 3. We're going to substitute that into our f function every place that there's an x. So when I square a square root, I get x minus 3 minus 2. So I have x minus 5. So for this one, since we have this square root here, our x value, we can't have a negative inside of our square root. So if we plug something into our g function, we need to make sure that it satisfies that there. Because if we get a negative here, then we can't substitute back into our f function because we get a complex number. So we need to make sure that we take care of this in our domain. So looking at x minus 3, x minus 3 needs to be greater than or equal to 0. So x needs to be greater than or equal to 3. So for our domain, we need to state that x needs to be greater than or equal to 3. We can write it in interval notation as 3 to infinity. In our final example, we're going to decompose a composite function. So we're going to take a function here, h of x, and we're going to split it up into 2, an f and a g. So typically, look at, try to find the most complicated. I know I have the square root, so I'm going to let that be my f function. So I have a square root of x, and then inside of that I have this x cubed minus 4. I'm going to let that be my g of x function. And I kind of work from the inside out. I saw that I had this x cubed minus 4 inside the square root, and that's kind of how I broke it down. So now if I worked it backwards, it should all work out.